Okay, so who is ready to start calculating probabilities? So we have talked a lot about the different types of probability that you see. We talked about some of the basic definitions, but now we're ready to start actually talking about calculating probabilities, all right? So that's what today is, just a lot of math problems, basically. A couple rules thrown in here and there. So when we're doing this, because again, our class is about how you use math kind of in the real world, a lot of this ends up kind of focusing a little bit on the side of gambling, okay? So if you are a gambler, then woohoo, and if you're not, don't worry, you don't need to have anything memorized or anything like that, but there is a lot of cards and dice that go on in this chapter, okay? So let's start with, let's start with the dice. Okay, so this time, we are going to look at a pair of dice. And we want to remember that when we calculate the probability of an event, the probability of an event is the number of outcomes in the event out of the number of outcomes in the sample space. Remember, it's a basic division problem. So once we know that we're talking about a pair of dice, this is going to guide us down to here, and that's where we need to figure out how many different outcomes there are in the sample space. So the idea is when you roll a pair of dice, you've got two six-sided die, so you can get a lot of different arrangements, right? So if we want to figure out how many arrangements there are in total, we're going to use what we learned in the last chapter using that pigeonhole method. So if we want to know how many arrangements of the dice, okay, then we're going to make two slots, one for each of our dice. On the first slot, there are 6 options for the first die, and then on the second die, there are also 6 options. Now remember what we're supposed to do with those two numbers? Okay, the fundamental counting principle says multiply them together. So there are 36 different options in total. So when you roll a pair of dice, there are 36 different arrangements that could come out. Now, that sets us up for the rest of our problems by giving us the denominator of our fraction. So now, if we're rolling a pair of dice, so we want to find the probability of getting a sum of 3 on the dice. Okay, so whatever game you're playing, Monopoly, whatever it is, you want there to be, you want to get 3. So you're rolling a pair of dice and you want to get 3. So what we need to do is we need to figure out what are the different ways that you could get 3 on the dice. So one of them is that one die could be a 1 and the other one would be a 2. Okay, is that going to give you a 3? And now because the two dice are actually separate entities, this one is actually another option. So 1, 2, and 2, 1 are actually 2 different options. Now, how about a 3 and a 0? Why doesn't that guy work? Okay, because remember, we're talking about dice here. So there is no 0 on the die. So don't get carried away and start making every arrangement that adds up to 3. You got to go with the numbers that are on the die. So on the two dice, there are only 2 ways that you could get a 3. So we could say that the probability of 3 is equal to the 2 options out of the total number of options, which is 36. And let's see, 2 divided by 36 gives us 0.056. Okay. So there's a 5.6% chance that you will get a sum of 3 on the dice. Okay. All right, let's do one that's a little bit bigger and uglier here. Let's say this time we want to find the probability of getting let's go with a 6. A sum of a 6. Okay, so we want the guys to sum up to be 6. All right, now 6 is a little harder. So we've got 1 and 5, right? That would give us 6, which also means 5 and 1. Then we would have 2 and 4, but also 4 and 2. Okay. And then we would have 3 and 3. Now, this one we do not flip around because both ways it's exactly the same. For the 3 and the 3, it means both die have to be 3. So this is only one option. Where these are flippity-flopped, because it could be one or the other. In this case, both of them have to be 3s in order for us to get a 6. Okay, but you see how that's all we've done is just made the different arrangements, thought about what would happen on the die, or on the dice. And so there are 1, 2, 3, 4, 5. So there are 5 ways to get a 6 out of the total 36, which gives us 5 divided by 36, 0.139. Okay, so 13.9% chance of getting a 6. Okay, one more of these guys. Make it a little bit more difficult here. This time we're going to roll 3 dice. Roll 3 dice. And I want the probability, so we're going to find the probability of getting 3 of a kind. So just mixing it up a little bit just to keep you thinking here. So first off, we're rolling 3 dice this time. So if we want to know how many different ways there are to do that, instead of just the 36, right, we're going to have to go 6 times 6 times 6, right, because our 3 dice now, which I believe gets us 216, but let's not just trust me, let's put it in there. Yes, I am correct, 216. So when you roll 3 dice, there are 216 different ways the dice could fall. Now, in this case, I want you to find the probability of getting 3 of a kind. Now we have to understand what that means. So 3 of a kind means that like they're all going to be 1s, or they're all going to be 2s, or they're all going to be 3s. Get the idea? All the way down until they're all 6s, right? So when they ask you for 3 of a kind or all of a kind, how many different ways can that happen? Okay, there are 6 different numbers on the die, so there are 6 different ways this could happen. So we say the probability of 3 of a kind is equal to 6 over 216. Here's my 6 divided by 216. And that gives us 0.028, okay? Or 2.8% chance of getting a 3 of a kind on 3 dice. All right, so we're getting the idea about how we're using the rules that we learned last time, in the last chapter, to find our total number, and then we're going ahead and calculating the probability. So this is kind of tying the two chapters together. But it's definitely important because we do need to know those numbers there. Okay. All right, now let's look at what we call the addition rule. So the addition rule and before we write down the addition rule, I don't think I did this definition last time when we had our last lecture, so we think we need this one. We need to talk about being mutually exclusive. So we say 2 events are mutually exclusive if they have no outcomes in common. Or another way to think about this is if we intersect two events or two sets together, we want their intersection to be 0. So this is taking us all the way back to the very couple first weeks of class, but it's the same idea here. Mutually exclusive or disjoint means that they have nothing in common, which means that there's nothing in their overlap. So if you intersect them, there's nothing there. Okay? Now that's important for the addition rule, because the addition rule says if two events are mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B. So if you're looking for one thing or another, so just a little reminder in notation-wise, this is union. So if you want the probability of A or B and they have no overlap, this becomes a straight addition problem, which makes life really easy, okay? So the easiest example that we use here is we're gonna go to the deck of cards, okay, which we have already discussed. So remember that if you're not up on your deck of cards, go to the internet, look up, get a visual of the deck of cards. But let's look at our deck of cards again. So I want to just draw one card from the deck. Okay, draw one card from the deck, and I want to find the probability that that card is a queen or a 2. So whatever game that we're playing, I'm waiting for the next card, and I am looking for either queens or 2s. That's what I'm collecting, okay? I don't know, whatever, it's go fish, whatever. So we want the probability of a queen or a 2. Now, remember that mutually exclusive means they have no overlap. So what we want to ask ourselves to start with is, are there any queens that are also 2s? And those cards are separate from each other, aren't they? So that means that we can find the probability of getting a queen, and we can just add the probability of getting a 2. The probability of a queen plus the probability of a 2. Okie dokie. Now, remember back to the deck. When we look at the deck, there are 4 queens in the deck, right? One of each suit. So there are 4 queens out of the total 52, yes? And then we're gonna add, now don't let that 2 throw you for a loop. How many 2s are in the deck? Okay. There are still 4, aren't there? So there are 4 2s out of the total 52. So together this makes 8 out of 52, which gives us 8 divided by 52, 0.154. So there's a 15.4% chance that you could get a queen or a 2, okay, when one card is drawn from the deck. Okay, let's look at another one here. How about if I want the probability of getting the 4 of diamonds or, let's see, what do I do here? Or a face card. Okay, so in this case, whatever game we're playing, we want the 4 of diamonds or a face card. Okay, the 4 of diamonds or a face card. Now, is the 4 of diamonds, does it have a face on it? It doesn't, does it? So these are mutually exclusive, which means that we can simply find the probability of the 4 of diamonds, and we can add that to the probability of getting a face card. Okay, so now I'm being very specific here. I want the 4 of diamonds. So that's one card, right? One card out of the whole deck. So there's 1 4 of diamonds out of the total 52. Now we have to remember about face cards. So remember that the king, queen, and jack are the ones that are face cards, and there are 4 of each. So it means that altogether there are 12 face cards in the deck, 12 face cards out of the total 52, which together gives us 13 out of 52. 13 divided by 52. Oh, hello, if we're thinking about this, 13 is a quarter, so this would be 0.25, okay? Or 25%. So there's a 25% chance that you get the 4 of diamonds or a face card, okay? Alrighty, so what happens though if the 2 events are not mutually exclusive? So let me just write up another example here. What if I wanted you to get or find the probability of getting a spade or a jack? A spade or a jack. Now, is there a jack of spades? Okay, there is, isn't there? So this is not mutually exclusive, which means there is most definitely an overlap, which means our rule that we have written up there no longer works, does it? So we got to do a little bit of manipulation on our rule, okay? So when things are not mutually exclusive, and the way this changes is, instead of this just being the addition rule, we call this the general addition rule, okay? And this just says to find the probability of A or B, we take the probability of A plus the probability of B, and we subtract the probability of A intersect B. Okay, so we subtract the probability of A intersect B, and that's that overlap. So in these 2 examples, there was no overlap, right? No overlap here. But in this example, there is going to be an overlap. Okay, so notice, no words about mutually exclusive or anything. So the addition rule, the general addition rule, whenever it says or here, it's an addition problem, but then you have to think about subtracting any overlap. So let's go ahead and look at this problem. So let me write it up again. The probability of a spade or a jack. So it starts by finding the probability of a spade plus the probability of a jack, and then it's going to subtract the one that's the overlap. So it's the probability of the jack of spades. And that is definitely the overlap. It's in both groups. All right, so thinking about the deck, a quarter of the deck is spades, so that's 13 out of 52. And then how many jacks are there in the deck? There are 4 jacks, 4 out of 52. Okay, now we come to the subtraction. So let me ask you, did the jack of spades get counted here? Okay, and it did, didn't it? Did the jack of spades get counted here? It did. So how many times have we counted the jack of spades already? We've counted it twice. Well, that's kind of cheating. It doesn't get to be counted twice, okay? It's not more special or anything. So because it was counted once here and once here, what we're gonna do is we're gonna subtract the over counting, okay? So by subtracting 1, it means that now the jack of spades only got counted 1 time. Okay, only got counted 1 time. So together there, so 13 plus 4 is 17 minus 1 will give us 16 out of 52, which will put us at 16 divided by 52.308. So there's a 30.8% chance of getting a spade or a jack. okay? And that requires that one so that again, that jack of spades doesn't get over-counted in the probability, okay? Okay, so let's look at one more here. Let's see, what do we want to find this time? Let's find the probability of getting a face card or a red card. Okay, so we want face card or a red card. Okay, so the first thing you ask yourself is, are there any face cards that are also red? And yes, there are, aren't there? So there most definitely are face cards that are also red. So what we're going to do then is we're going to go the probability of a face card plus the probability of a red card. But then we're going to subtract away the probability of the red faces. Okay, and that's the overlap, right? The ones that are both red and have faces on them. Okie dokie. So we've said before, there are 12 face cards in the deck, so we start with 12 out of 52. Then half of the deck is red, so we could say 26 out of 52. Okay, so face cards plus the red cards. But now we got to remember how many of those red cards, of those 12, of those face cards are also red. So, and that's half of them. So there was 12, that means 6 of them are going to be red, aren't they? Now, did those red face cards get counted here? Yep. Did they get counted here? Yep. So they got over counted. So we will subtract away 6 out of 52 so that they only get counted one time. So we're not over, giving an overestimate of the probability. So let's see, that'll give us what, 32? 32 over 52. Which gives us 0.615. So there is a 61.5% chance that you will get a face card or a red card. Okay. All right, so what you're practicing to start off with is this addition rule, deciding when it's mutually exclusive, and then what you do when it's not mutually exclusive. And remember, you can do both problems, you just have to think about it. Remember, probability always requires like an extra step of thinking. Don't just go, oh, that's easy, and write down the answer. Go, wait a minute, is there one more step? Is there something I should think about? Because normally there is when it comes to probability. Okay, so that's the first part of calculating probabilities. I will come back for part 2 in a little bit, okay? But start with this, and then we'll be back for the second part. Okay?